Good morning, students. Last class we done about imperfections or defects in solids. Today is about the electrical properties of solids. Electrical properties of solids. Most of the solids are having the conductivity range between 10 raised to minus 20 to 10 raised to 7 Simon meter inverse. We know Simon meter inverse is the unit of conductivity. Okay, so most of the solids are having the conductivity range between 10 raised to minus 20 to 10 raised to 7 Simon meter inverse. Okay, so based on this conductivity, the solid substances are classified into three. All of you know that many times the terms we used. Okay, so first one is conductors, and the second one is semiconductors, and the third one is insulators. Okay, based on the conductivity, the substances are mainly classified into three types. First one is conductors, second one is semiconductors, and the third one is insulators. Okay, so conductors means they will conduct, the conductivity of that substance will be high. Okay, and their conductivity range will be between 10 raised to 4 to 10 raised to 7 Simon meter inverse. Okay, so they will have high conductivity. Example for that is metals. Metals are very good examples for which were conductors. Next is semiconductors. Semiconductors means they are having the conductivity, moderate level of conductivity, not very high and very low. Okay, and the conductivity range is between 10 raised to minus 6 to 10 raised to 4. Clear? Then the last one is example for semiconductors. What is a germanium, silicon, etc. Insulators. Insulators means what? They do not conduct what? Electricity, and the conductivity is very low. We can say most of the time they will not conduct only, and that is they are having the conductivity range 10 raised to minus 10. It is very low to 10 raised to minus 20. Okay, Simon meter inverse. Okay, so conductors means they will have high, semi means moderate, and insulators means very low, or sometimes they will not conduct. Insulators, example for insulators, all of you know, plastics, polymers, etc. So that is based on the conductivity. Solids are classified into conductors, semiconductors and insulators. Clear? Okay. To explain the conductivity, the electrical conductivity or conductivity properties are explained by one theory is there, that is known as band theory. What is the theory? The conductivity in solids are explained by a theory that is known as band theory. Okay, so this band theory is having 8 postulates. Okay, how many postulates are there? 8 postulates are there. So first one is, we know atomic orbitals are there, molecular orbitals are there, right? So first one is, in solids, the outer atomic orbitals undergo linear combination to form molecular orbitals. We know internuclear axis overlapping is there, sideways overlapping is there, and we will get molecular orbitals. Last year we explained in chemical bonding chapter. Okay, so here what is the first postulate is the outer atomic orbitals undergoing linear combination, combining along the internuclear axis, we will get the molecular orbital. That is the first postulate. Okay, and the second postulate means this molecular, the energy, the group of same energy level is known as a band. Okay, a group containing same energy levels, or the same energy levels are arranged in a group known as what? Band. B-A-N-D, band. That is known as a group of having same energy levels is known as what? Band. Okay, so third postulate is, these molecular orbitals are having almost same energy. They grouped or crowded together form a band of molecular energy. Okay, so what is the third postulate? These molecular energy levels form, they are almost having same energy. They will group together or crowded together form a band of molecular orbital energy. Clear? That is the third one. And the fourth one is very important. Okay, and there are two types of band is there. Okay, one is valence band and the second one is which one? Conduction band. First one is which one? Valence band and the second one is conduction band. Okay, first one is valence band. Okay, and the second one is conduction band. Conduction band. So valence band means the highly occupied energy band is known as which one? Valence band. Okay, so which one is? It is the highly occupied valence band. Highly occupied band is known as valence band, and the low unoccupied energy band is known as which one? Conduction band. Okay, so valence band means it is a highly occupied energy band is known as valence band, and conduction band means it is the low unoccupied band is known as what? Conduction band. Okay, so there are two types of band that we will explain detail later. Okay, there are two types of band, valence band and conduction band. Valence band means it is a highly occupied energy band. Okay, and conduction band means it is a low unoccupied energy band is known as which one? The conduction band. Okay, so that is the fourth point. It is the highest occupied band is known as valence band and the lowest unoccupied band is known as conduction band. Okay, and the electrons present, next postulate is the electrons present in the conduction band is responsible for the conductivity of a solid material. So which one is responsible? The electrons present in which band? Conduction band is responsible for the conductivity of any solid substance. Clear? That is the sixth postulate. Then the seventh postulate is very important. The gap between conduction band and valence band is known as forbidden zone or energy gap. What is it? There is a gap in metals. Two band is there, conduction band and valence band. Okay. So suppose this is the valence band. Which one? Valence, because it is highly occupied one. Valence band. Okay, and this is the conduction band. Okay, this is the which one? Conduction band. Conduction band. Okay, and you can see here there is a gap, right? Okay, so the gap between this valence band and conduction band is known as forbidden zone. What is it? Forbidden zone or energy gap. Forbidden zone or energy gap. Okay, so what is forbidden zone or energy gap? It is the gap between or energy separation between conduction band and the valence band is known as which one? Forbidden zone or energy gap. Clear? So that is about which one? That is the seventh postulate. Okay, so that next is eighth postulate. This is just the repetition of the all conclusion of all the postulates. Okay, eighth one, the conductivity mainly depending upon four factors. How many factors? The eighth postulate is telling about the conductivity of solid substance mainly depending upon the four factors. How many factors? Four factors. Okay, so the first factor is partially filled valence band. First one is which one? Partially filled valence band. I will explain next. Okay, next is coming, that is detailed. It is coming how it is partially completely filled and all. Okay, so mainly the conductivity depending upon four factors. First one is partially filled valence band. Second one is overlapping valence band and conduction band. Overlapping valence and conduction band. Then third one is narrow forbidden zone. Narrow means what? Very small forbidden zone. And the fourth one is wide forbidden zone. It may be big one or small one. Okay, small means it is known as narrow and big means it is known as what? Wide. Okay, so that is the four main factors according to which theory? Band theory. What are the four factors depending on the conductivity? First one is which one? Overlapping valence band. Not overlapping. First one is partially filled valence band. Second one is overlapping valence and the conduction band. And the third one is narrow forbidden zone. And the fourth one is wide forbidden zone. Okay, so that is about which one? The postulates of band theory. Okay, it is having how many postulates? Mainly 8 postulates are there. So once again I will tell you in short the postulates. Okay, first is what? Atomic orbitals combined together, atomic orbitals undergoing linear combination, we will get molecular orbitals. Next is the group of the energy levels are known as band. Okay, so the molecular orbitals are having almost same energy. They crowded or grouped together form a molecular orbital band. And there are two types of bands are there: valence band and conduction band. Okay, the highly occupied energy band is known as valence band, and the lowest unoccupied band is known as the conduction band. And the electrons present in the conduction band is responsible for the electrical conductivity or conductivity in solids. Okay, then there is a energy gap or energy separation between the conduction band and which one? Valence band is there, that is known as the forbidden zone. Okay, and there are four factors that depending upon the conductivity is. First one is which one? Overlapping. First one is partially filled valence band. Second one is overlapping valence and conduction band, and the third one is narrow forbidden zone, and the fourth one is which one? Wide forbidden zone. So that is about which one? Band theory. Okay, band theory. Clear all of you? Clear? Okay, that is about which one? The band theory. Clear? Next is conductivity based on band theory. Okay, based on band theory, how we can explain the conductivity? First is conductivity metals. How it is we can? Metals means what it is? Conductors. So conductivity in metals or conductors. Okay, so how we can explain? So we know there are two, according to band theory, there are two types of bands are there: conduction band and valence band. So in case of metals, how it is means they will have partially filled valence band, and here is the conduction band. We know the highest occupied band is known as which one? The valence band, and the unoccupied band is known as conduction band. There is no electrons, okay, in conduction band now. Only the electrons will be occupied in the valence band. Okay, so in case of metals, there is a partially filled valence band. It is not completely filled band. Valence band is not completely filled, it is partially filled here. That is why it is here. Maybe just to show you this much. Okay, and here it is the conduction band. And metals they will have also like the overlapping conduction band and valence band. Okay, so conduction band and valence band may be overlap. Here you can see they are overlapping. Okay, so in conductors or in metals there will be a partially filled valence band and there will be an overlapping conduction band and valence band. Okay, so what will happen is when the voltage is applied, these electrons will be there in which one? The valence band. It is partially filled now. So the electrons will excite to this place, the same band, excite to the same band, or it can be excited which one? The conduction band. Okay, so when the voltage is applied, the electrons will be excited to the same partially filled valence band or to the conduction band. Okay, and these electrons in the conduction band or this band is responsible for which one? The conductivity in conductors. Okay, so what is happening when voltage is applied? The electrons will excited to the same valence band because it is place is left, or the conduction band. Okay, so these electrons are responsible for, these electrons will move to the positive terminal. We are applying voltage. Okay, so battery is the positive terminal and these electrons are responsible for the conductivity in case of metals. Okay, And when the temperature is increased, what will happen to the conductivity of metals? Okay, we know in metals there is a positive kernel. Positive kernel means what? Positive charge surrounded by sea of electrons is there, right? Okay, so in case of metals there is a positive kernel will be there. These positive kernels will be vibrating. Okay, when the temperature is increased, that the vibration of these kernels increases. So that is why it prevents the free movement of electrons and increases the resistance. So resistance increase means what will happen? Conductivity decreases. Conductivity decreases. So what is happening when temperature increases? What will happen? The resistance increases and the conductivity decreases in case of which one? Metals or conductors. Clear? So in metals what is happening? It is having a partially filled valence band and a conduction band, or overlapping valence band and conduction band. Okay, then voltage is applied. The electrons will excited from the valence band to the same valence band or to the conduction band, and these electrons are responsible for the conductivity in conductors. When the temperature increases, what will happen? The kernels, because of the kernels, the vibration of the kernels increases. That is why it prevents the free flow of electrons. So resistance increases and conductivity decreases. Conductivity decreases. But in case of, okay, so that is about, they will ask, explain the conductivity in conductors or metals based on band theory. So you have to draw these diagrams and you have to explain this much. Next is the conductivity in semiconductors based on which one? Band theory. Semiconductors, it is how it is means, this is conduction band and this is the valence band. The energy gap between, we know that is known as forbidden zone, is very small. Small means very narrow, around 50 to 300 kilojoules per mole. Okay, so in case of semi, you have to draw the diagrams. They are asking the question. Okay, so that is just to draw two bands, and the energy gap between these two, conduction band and valence band, is very small. Okay, so room temperature itself, the electrons can jump from valence band to conduction band to conduct the electricity. To conduct. Okay, so easily the electrons can jump from here to here. But when temperature increases, what will happen is more electrons. As usual in normal temperature they will conduct, because the gap is very small, no? Okay. But if the temperature is increases, what will happen? More electrons will jump or excite from valence band to conduction band. So electrons are more means what will happen? The conductivity increases with the increase in temperature in case of semiconductors. Example for semiconductors, we know germanium, silicon, etc. Right? Example for conductors, all the metals. Okay, all the metals are conductors. So here energy gap, in case of silicon, the energy gap is found to be, this energy gap is found to be 111, okay, 111, and for germanium it is 63 kilojoules per mole. Okay, in case of silicon and germanium, this is the energy gap value. Okay. So in semiconductivity, in case of pure semiconductors or pure substances, is known as intrinsic semiconductivity. Okay, so semiconductivity in case of pure substance like germanium and silicon, it is a pure semiconductor. Okay, that semiconductivity in pure substances are known as which one? Intrinsic semiconductivity. That is known as intrinsic semiconductivity. Intrinsic. That is known as intrinsic. So intrinsic means what? The conductivity in case of semiconductivity exhibited by pure substances is known as what? Intrinsic semiconductivity, and it is found in which one? Germanium, silicon, etc. That is found in germanium, silicon, etc. Okay, so example for intrinsic semiconductors, which one? Germanium and silicon. So it is found in which one? The pure semiconductivity exhibited by pure substance like germanium and silicon is known as which one? Intrinsic semiconductivity. Next I am moving to extrinsic semiconductivity. What is extrinsic semiconductors? Extrinsic semiconductors. So first is we done intrinsic semiconductors, and next is extrinsic semiconductors. What are extrinsic semiconductors? Actually, the semiconductivity of intrinsic semiconductors or pure semiconductors, it is very low, and no practice is not having. We cannot use practically this conductivity. We cannot know practical use, okay, because it is very low. So to increase the semiconductivity of intrinsic semiconductors, we are adding a special type of elements as impurities, okay. So what is that? To increase the semiconductivity or to increase the conductivity of intrinsic semiconductors, we are adding a special types of elements as impurities, okay. That process is known as what? Doping. So what is doping? It is a process of increasing the conductivity of semiconductors, intrinsic semiconductors, by adding some elements, some special elements, okay. That is known as, that process is known as what? Doping, and that special elements we added to increase the conductivity is known as dopants. What is it? Dopants. To increase the conductivity is known as dopants. That process is known as doping, okay. So mainly we will add two types of the dopants added may have high or lower valency than the host ion. Host ion. What is that means? Suppose we are doing silicon Si. Silicon is a intrinsic semiconductor, right? Okay. To increase the conductivity of silicon, we can add phosphorus. Sb means what? Antimony and arsenic. Okay. Or we can add boron, aluminium, gallium, etc. Boron, aluminium, gallium, etc. So here phosphorus, antimony, arsenic is having higher valency than which one? Silicon. And these are having lower valency than silicon. Okay. So we can add the dopants which are having higher or lower valency than the which one? The host. Which one is the host here? Silicon. Which one is the host here? Silicon. Okay. So the process, what is doping? Doping means the conductivity of intrinsic semiconductors is increased by adding special elements as impurities. That process is known as what? Doping, and special elements we are added is known as dopants. Okay. So the dopants may have higher or lower valency than which one? The host ion. For example, silicon, phosphorus, antimony and arsenic having higher valency than silicon, and boron, aluminium, gallium is having lower valency than which one? Silicon. Clear? So based on which dopants we are adding, there are two types of extrinsic semiconductors. Based on which dopants we are adding, there are two types of extrinsic semiconductors. There are two types is there. First one is N-type semiconductor, N-type extrinsic semiconductor, N-type extrinsic semiconductor, and the second one is P-type extrinsic semiconductors. Okay. So N-type extrinsic semiconductors means what is N-type and what is P-type. Okay. For example, we know silicon is our intrinsic, that is the host. Okay. So if you are adding N-type, in this case we are adding doping with phosphorus. Phosphorus you can use, arsenic or antimony I am showing with phosphorus. Okay. So in N-type we are using the dopants having higher valency. Dopants having higher valency, like which one? Phosphorus. Okay. So phosphorus is having the valency 5. Phosphorus is having the valency 5. Okay. So if we are adding phosphorus, so this phosphorus will combine with one silicon, second and third, fourth. Then the phosphorus, the fifth valency, fifth one electron is there. Phosphorus is having 5 valency. So 5 valence electrons are there. In that 4 valence electrons are used for forming bond with 4 silicon atom. Okay. But the last one, fifth electron is not used there. Okay. So here the conductivity is due to the migration or due to the movement of electrons, because here electrons are free. One electron is free. So the conductivity is due to the migration or movement of these free electron. Okay, so that is why it is known as what? N-type extrinsic semiconductors or N-type semiconductors, because the conductivity in this case is due to the presence of negatively charged electrons. That is why it is known as what? N-type semiconductors. Clear? Okay, so that is N-type. But in P-type semiconductors, what is happening is we are doping. The dopants used here is having lower valency than the host. Okay. For example, silicon atom is the host, and we can use which one? Boron, aluminium, gallium. So here I am using boron. Boron is having valency only 3. Okay. But silicon is having 4. Okay. Here phosphorus is having 5, but silicon is having 4. So here the dopant is having valency lower than that of which one? The host ion. And in this case, the migration. In this case, the conductivity is due to the movement of positively charged holes. HOLES. Positively charged holes. Here it is negatively charged electrons. That is why it is known as N-type. Here P-type means it is the conductivity is due to the presence of which one? The positively charged holes. That is why it is known as a P-type semiconductor. Okay, so how the conductivity here is, we are using boron, right? Okay, and boron is bonded to, it is having valency how much? It is having valency 3. Silicon, silicon. But we know boron, silicon is having valency how much? 4. So here there is one more silicon is there, right? Okay, and here silicon is having electron, but boron is not having electron. That I am marking as a hole. That I am marking as a hole, and that is known as what? An electron hole. What is it? It is an electron hole, and it is having a conductivity of which one? Then it is having a charge positive. Okay, so first this is, if you are considered here, one positively charged electronic hole is there, and this hole is filled by next boron, silicon will be there, here silicon will be there, here silicon will be there, here what is there? Silicon. Here one hole will be there, but here one electron is there. Silicon is having one electron, right? Next, that free electron will come and fill here. So what is happening? So this is filled. Which one? Electron hole is filled by the next silicon atom. And next it will be continuing. Okay. So the conductivity is here because of this electron hole. The electrons will migrate from here to here. Okay, so the conductivity is due to the presence of which one? The positively charged electronic hole. The positively charged which one? The electronic hole. So that is why it is known as a P-type conductor. So the electronic hole will move this direction. No, electrons will move this direction. Hole will move that direction, right? Here already one hole is there. Here hole is there. So the electron will come here and fill. Okay, so next hole is here, and electrons from next one will come and fill here. So what is happening? The electrons will move from here to here, but the hole will move from here to here. Here to, the first it was here, it is filled by the second silicon atom. Okay, so that here hole is filled, but the electrons is moved from there to here. And the hole, next here one hole will be generated, and it will be filled by the next one. So the holes, the electronic hole will be moving from this direction to this direction, from left to right, but the electrons will move opposite to that, that is from right to left. So because of the movement of these electronic holes, what is there? The conductivity is there in case of P-type conductors. Okay, so we know here the electrons are having what? Negative charge. So it will move to the positively charged electrode, and the holes are having positively charged. It appears to move to the negatively charged electrode. Okay, so that is about which one? Semiconductors. There are two types of extrinsic semiconductors, that is N-type semiconductors, and next one is which one? P-type semiconductors. Clear all of you? Next is the difference between N-type and P-type semiconductors. Okay, I already explained, just 3 difference you have to know. First is in N-type, we know we doped with which one? Phosphorus, that is which higher valence elements or atoms. Okay, so generally they are known as pentavalent. I already told you phosphorus is having how much valency? 5. That is why doped with pentavalent atoms. But in case of p-type, we know we doped with which one? Boron, aluminium and gallium. So they are which one? Trivalent. Boron is having what is the valency? 3. That is why we are doping with which one? Trivalent. So in n-type doped with pentavalent, and in p-type it is doped with trivalent, right? And in n-type the conductivity is due to the presence of electrons, negatively charged electrons, but in p-type the conductivity is due to the presence of positively charged holes. Okay, then in this case n-type we know the silicon, it is for doping we are using phosphorus, arsenic means As, antimony means Sb. Okay, generally we are using phosphorus, arsenic and antimony, but in case of p-type we are using boron, aluminium and gallium. So these are the three differences. Any three differences enough between n-type and p-type. Okay, so last one is conductivity in insulators based on band theory. Very easy. So here you can see from this diagram, this is conduction band and this is the valence band, and the energy gap between this conduction band and valence band is very high compared to which one? The semiconductors. Okay, so it is very high, so it is very difficult to move or the electrons from which one? Valence band to conduction band, and that is why insulators are very bad conductors. Why it is? Because the gap between the energy gap or forbidden zone between valence band and conduction band is very large. So it is not easy to move the jump or excite the electrons from here to here. So that is why they are acting as the very bad conductors of electricity, right? And normally they will have the conductivity value 10 raised to minus 20 to 10 raised to minus 10 Simon meter inverse. Okay, so that is based on the band theory. We classified the substances into which one? Conductors. In conductors, what is there? The valence band, partially filled valence band, or overlapping valence band and conduction band, right? But in semiconductors, what is there? The band, the energy gap between valence band and the conduction band is very narrow, very small. Okay, but in case of insulators, what is there? The band, the gap or forbidden zone between the conduction band and the valence band is large. So that is why the excitation of electrons is not possible. That is why there is now they are having low conductivity. So that is about which one? That is about the conductivity in based on the band theory. Clear all of you? Clear? Thank you girls.